Hello students, welcome back to another session. So here we are going to see enthalpy and humid specific heat. These are the two psychrometric properties we are going to see here. And in the earlier session, we have seen degree of saturation and relative humidity. Already we have seen specific humidity and dew point temperature, Gibbs-Dalton's law, properties of moist air, and now we are going to see enthalpy and humid specific heat. Next, we are going to see wet bulb temperature and thermodynamic wet bulb temperature, psychrometric chart, psychrometric of air conditioning processes, mixing of air streams. So these are the topics left out. In next session we are going to see wet bulb temperature, and then we will complete the four topics in four consecutive sessions. Now we are going to see enthalpy and humid specific heat. So enthalpy of moist air, according to Gibbs law, the enthalpy of a mixture of perfect gases is obtained by the summation of the enthalpies of constituents. So whatever is the constituents which forms the entire mixture, so we have to consider the enthalpy of all those constituents. Thus, the enthalpy of moist air H, so we are going to denote this enthalpy with letter H, is equal to the sum of the enthalpies of dry air and the associated water vapor. So that is H equal to HA plus omega HV. So this is the simple H formula, that is enthalpy formula. So per kg of dry air, where HA is the enthalpy of the dry air part and omega HV is the enthalpy of water vapor part. So we are considering this as two parts. One is dry air part and another one is water vapor part. So now omega HV is the enthalpy of water vapor part and HA is the enthalpy of dry air part. So dry air enthalpy. So first one is dry air enthalpy. Considering the change in enthalpy of a perfect gas as a function of temperature only, the enthalpy of the dry air part above a datum of 0 degrees Celsius is expressed as, so HA equal to CPAT equal to 1.005 T. So that is in terms of kilojoules per kg. So where CPA equal to 1.005 kilojoules per kg degree Kelvin is the specific heat of dry air. So specific heat of dry air. So this value you have to remember this, student. When you solve the numerical problems, it will be very handy, and you can easily remember this value. 1.005 kilojoules per kg Kelvin. T is dry bulb temperature of air in terms of degree Celsius. In imperial units, we are not using this, but still you please aware of it. HA equal to 0.24 T BTU per lbm, where T is in Fahrenheit, degree Fahrenheit. So next one is water vapor enthalpy. So this is the taking reference state enthalpy as 0 for saturated liquid at 0 degree Celsius. The enthalpy of water vapor, that is at point A in figure, is expressed as, I will show you that figure, HV equal to HA. So that is equal to CPWTD plus HFGD plus CPVT minus TD, and this is where the CPW is the specific heat of liquid water and TD is the dew point temperature, and HFGD is the latent heat of vaporization at DPT, dew point temperature, and CPV is equal to specific heat of superheated vapor, and T is equal to dry bulb temperature, and this figure you can see here. So this is the G point A to B, and this is G at 0 degree Celsius. So evaluation of enthalpy of water vapor part. So this is water vapor part, and reference state is saturated liquid at 0 degree Celsius. So reference point is 0 degree Celsius. So this is the reference state. And point A, start of superheat. So this is point A. From here the superheat starts. So C is A, C to A. So C to A, this curve is saturated state. So this curve is said to be saturated state, and A to B. So from here to here, this is superheated state. So this is saturated state, and then we have superheated state. And this thermodynamic path is used for the entire study of this water vapor enthalpy. So say, taking CPW, that is equal to 4.1868 kilojoules per kg, and CPV is equal to 1.88 kilojoules per kg degree Kelvin, and water heating from 0 degree Celsius to temperature, that is the maximum temperature, HV, that is equal to, we have 4.41868 kilojoules, that is TD plus HFGD plus 1.88 T minus TD. And note to note this expression can be lengthy for practical calculations, and instead two simplified approximations are widely used. So those are method 1, HA equal to HC, that is equal to H of G into D, that is H of G of D, and method 2 can be HA equal to HB, that is equal to H of G at 0 degree Celsius plus CPV T. So these are the two relations, and with which we can easily calculate the enthalpy of air, moist air, taking the latent heat of vaporization of water at 0 degree Celsius as 2501 kilojoules per kg, we get HV, the final HV. So this can be reduced to HV equal to 2501 plus 1.88 T, that is in terms of kilojoules per kg. So imperial units we don't require, but still you can see HV equal to 1061 plus 0.444 T, where T is in Fahrenheit, not Celsius. So final expressions of enthalpy of moist air can be reduced to H equal to 1.005 T plus omega into 2500 plus 1.88 T, that is kilojoules per kg of dry air. In imperial units we don't require, but this is reduced to this equation in imperial units. And this formula is widely used in psychrometric calculations, air conditioning system design, and HVAC analysis. So this formula is very important formula. All of you should remember. And anyhow, we are going to solve problems on this. We will discuss how to use this formula when we have to calculate the enthalpy of moist air. So the enthalpy of moist air gives a measure of total heat energy and is essential in cooling and heating load calculations. So and also the enthalpy of moist air gives a measure of total heat energy and is essential in cooling and heating load calculations. So next property. So already we have seen the enthalpy of moist air. Now we will move to humid specific heat. So this is another psychrometric property. So equation for the enthalpy of moist air can also be written in the form, so H equal to Cpa plus omega Cpvt plus omega H of G at 0 degree Celsius, and this can be reduced to Cpt plus omega H of G at 0 degree Celsius. So where Cp is equal to Cpa omega Cpv, so this formula we can use for this CP calculations. So that is 1.005 plus 1.88 omega in kilojoules per kg dry air Kelvin. So in terms of imperial, you can reduce to this. So humid specific heat is this is termed the humid specific heat. So it is the specific heat of moist air, that is 1 plus omega kg per kg of dry air. The term Cp governs the change in enthalpy of moist air with temperature at constant specific humidity. The term omega HFG at 0 degree Celsius governs the change in enthalpy with the change in specific humidity. So that is due to addition or removal of water vapor in air. So since the second term 1.88 omega is very small compared to the first term 1.005, so as an approximated Cp value can be 1.0216 kilojoules per kg of dry air Kelvin, may be taken for all practical purposes in air conditioning calculations. So we are going to use this for load calculations also. So we will see one example on this moist air analysis at 21 degree Celsius. So now a mixture of dry air and water vapor is at a temperature of 21 degrees Celsius under a total pressure of 736 mm of Hg. The dew point temperature is 15 degrees Celsius. Find partial pressure of water vapor. We have to find all these parameters. So relative humidity and specific humidity, specific enthalpy of water vapor by three methods, enthalpy of air, specific volume of air per kg of dry air. So these are the six parameters we have to find. So first one, partial pressure of water vapor from steam tables. So you have to carry these steam tables with you to exams, and you have to effectively use it, and I will be teaching that when we meet in our regular classes. And from steam tables, partial pressure at 15 degree Celsius dew point temperature, so PV equal to 12.79 mm of Hg. So that is equal to 12.79 into 133.3 divided by 1. So that is equal to 1707.5 Newton per meter square. So that is the partial vapor pressure. And now saturation pressure. So next parameter to find in this problem, saturation pressure of water vapor at 21 degrees Celsius, so dry bulb temperature. So Ps is equal to the specific pressure, that is equal to 18.65 mm of Hg. So that is equal to 18.65 into 133.5. So that is equal to 2489.8 Newton per meter square. So third parameter to find here, relative humidity. So we know that relative humidity pi equal to PV by PS into 100, and we know the PV and PS, that is equal to 12.79 divided by 18.65 into 100. So that is equal to, in terms of percentage, 68.58%. Specific humidity omega equal to 0.622 PV by PA, that is equal to 0.622 into 12.79 divided by 736 minus 12.79. So that is equal to the 0.011 kg of water vapor per kg of dry air. So latent heat of vaporization of water, that is equal to HFG at 21 degrees Celsius is equal to 2452. So this is we have to find from tables, and kilojoules per kg. HFG at 15 degrees Celsius is equal to 2466.2 kilojoules per kg. And specific enthalpy of water vapor. So using three methods, we can do it in three ways. And method C, that is equal to HC equal to 4.1868.21, that is the plus 2452, so that is equal to 2540 kilojoules per kg of water vapor. And method A, HA is equal to 4.1868 into 15 plus 2466 to 66.2 plus 1.88 into 21 minus 15, that is equal to 2540.3. So it is almost the same. So method B, HB is equal to 2501 plus 1.88.21, so that is equal to 2540.5. So almost the same. So using three methods we can found, and you note that the three values are extremely close to each other. So all three methods results in same values, almost the same, and almost in fractional values it differs, but it is considered to be same. So next, the sixth parameter, enthalpy of moist air. So using this relation, H equal to HA plus omega HV equal to 1.005 into 21 plus 0.011 into that is 2540.5. So that is equal to 49 kilojoules per kg of dry air. So next one, a specific volume of air V equal to VA. So RA by T into PA. So that is equal to 287.3 into 273 plus 21 divided by 723.21 into 133.5. So that is equal to 0.875 meter cube per kg of dry air. So that is all parameters we have find out from for the given problem. Now coming to end the textbooks, please refer as I said earlier, CP Aurora. CP Aurora gives you the complete picture of this topic, and all psychrometric properties. I recommend you to refer CP Aurora textbook, and also you can refer for additional information the Kurmi, Rajput and other books, and we have NPTEL material and other materials, online materials. You can refer this for additional information, students. We stop here. We will meet again in next session. Thank you.